All right. Success. For the assignment, can we take up, down, left, right input from the user to make moves? Yeah, sure. Again, that part's not really well defined, right? So assignment one, I say Sneaky Pete should make it to the end. So you can implement some AI or you can implement a user interface if you want, right? So using the arrow keys or whatever, have them move across. Make sure you detail that in your README so that the TA knows what they're looking at. But yeah, absolutely. That part is meant to be not really taken too seriously. Just, have some fun with it. And as long as you try something, you'll get your marks for that part. All right. So other questions on the assignment before I, yeah. Yeah, it's basic stuff, right? So if you didn't do anything special, just list your files and compile instructions. That's it. Compile and run instructions. What is it? Yeah, the command, exactly. Which commands you would use. Yeah. Because like maybe, not for what we're doing, but maybe you need a special flag or something, right? Because maybe you use the math library. So we want to know that. Yeah. All right. Yeah.
Instructions it says like open files, but like I don't see that anywhere. I'm basically supposed to create.
Oh, I gave you some file, didn't I? Okay. Yeah. Just rename it to sneaky one. Yeah. Yes. So once you're done part one, you just make a copy and copy it into part two, and then keep. Yeah, you start from the same base code and then make adjustments. And then part three, you might have to change like some function signatures and stuff like that. But again, you're going to start from whatever you created in part two. And if you don't get part two done, right, that's okay. Just work on the taking the input part in part three. Yeah. Yes, please. Yeah, it's just easier that way. So then you can kind of showcase what you did for that part, right? So that's the idea. So if something's not working, you can comment it out in, if part two you didn't get working, you can comment it out in part three. There's another question. Yeah. Pardon? Oh, like you're going to demo it for a TA? Is that not? I hadn't planned on it. I mean, they're going to run it. Yeah. 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 I'm sorry. I'm sorry. I can't. I'm old and yeah.
You have to also write the print map function.
Was that built in? I don't remember. Should I give it to you? I think it's there.
Not there.
It's not there. You have to.
It doesn't say to build it, but you have to build it yourself.
Yeah. So
I didn't put the print map function in. Oof. Okay. My apologies. But if you've built it already, that's great. It's not super difficult. Yeah, okay. Yeah, sorry. Good you brought it up. I did mean to include it. I'm not sure if I deleted by accident or what. Yeah. Well, I added, yeah. I'll add it. I'll update the bright space and then I will make an announcement saying you can pick up your new function if you want. All right. Other questions? Okay. All right. So almost we'll almost get 80 minutes in this class, maybe 70, but that's better than last time. We are here on the 17th. So we're gonna bitwise, we're behind that. We're about a lecture behind, but with good reason because I introduced some stuff, right? So it's not, we are sort of keeping a good schedule. It's just quite the schedule here. Of course, the second tutorial and assignment one are due this weekend, and then assignment two and tutorial three will be released by Monday. So yeah, so that's where we stand right now. Questions on that? Okay. All right, so last class we were talking about that's not what I want. It's not really what I want either, I guess. All right, well, whatever. I guess that'll work. So last time we were talking about arrays. So we had mentioned something about, um, how we implement arrays, the syntax behind it. Basically, I could declare an array when I pass it as a parameter using an explicit array declaration. But what we talked about is actually it's also a pointer, right? So this is pointer syntax. So pointers are a big deal in C. We're going to use quite a bit. And so yeah, this is sort of an introduction to that. And so that was one thing we looked at. The other thing we looked at is we had, an application here, a function where everything was in the main function. And then we started taking some stuff out of it to make into separate functions. And we ended up with, instead of that big long function in main, we had broken it down into some smaller functions that were sort of, logically consistent, right? So everything I do in get array data is just that has to do with that one purpose of getting array data and entering it into the array. Okay. So yeah, that's where we left off. I do want to go over this idea of pass by reference and pass by value. So as mentioned, this is maybe not quite exactly what we just looked at, but we had a function that took in an array and also an int. And it turns out this array is a pointer, but this is just an int. And we're passing the int by value and we're passing the array by reference. So when we say reference, what do we mean? Well, we mean instead of making a copy of the variable and all of the values it contains, we just pass in the memory address, right? So then the function that I call now has access to that array. So for example, if I have my main function here, can you guys see that okay? Maybe I'll turn down the lights a bit. Somehow here. Okay. Just let me know if you have trouble seeing that. So I have my main function. I declare an array of size 8, which I see here, right? So it starts here, and then I have 8 memory locations. And then I declare an int size that has a value of 8, right? So we'll put a little 8 in there. And those are, so this is in some sense, this is the function call stack, right? Or just the stack. So it contains all local variables, in this case, that I've declared in main. Now from main, I call display array, and I pass in array and size as arguments, right? And this is my display array function here. And it just does some, whatever, it just does some, I don't even care really what it does. It prints out part of the array, but I mostly care about the parameters I'm passing in. Okay, so size is 8. In my original function, the array, I didn't initialize it, so it has garbage is left there. When I call display array, what I pass in is actually, I don't pass in the entire array. I pass in the memory address where it starts, right? So in this case, array starts at 0, 0. So this would be sort of the value that I pass in for the first argument. And the second argument is an int. And so I make a copy of this one, right? So I'm just going to pass in the value 0, 0, which is a memory address, and the value 8, which is an integer. So now my array gets a copy of the memory address, right? So that's this parameter. And the array size gets a copy of the value that was in size. Okay, and now when I run it, well, the first thing I do is the array size, I decrement it by 1, which means that this goes down by 1. But you'll notice it has no effect on the variable that I used to call the function, right? I made a copy of that variable, and now when I change that copy, it doesn't affect the original. However, when I do something like maybe I print the array size, well, what at the array size? So what I do is this is integer to the beginning of the array, and then I use what value I pass into the subscript, which is now 7, to return whatever values in this location, right? So I count 7 up from, or yeah, basically starting with 0, I count up to index 7 in my array, and then that is what gets printed out. So I'm printing out a variable that's actually in the previous function call stack. And if I happen to say, do something like the array, well, maybe I assign it a new value equals 10, then that 10 would go in here. And when I return from my function, this gets popped off. So all of that information is lost, but any changes I made to the array are still in effect. Okay, so that is passed by reference. I pass in the address of a variable, and then when I use it, I'm using the actual variable. And pass by value, well, I'm making a copy of the variable, and when I change the value in that, it does not affect the original. Okay, so that's passed by value, passed by reference. Questions? Okay. Seems like really, yeah. Memory address, right? So you can kind of see them here. I wrote little tiny memory addresses up the left-hand side there. Okay, so then 00 represents, I guess it's it's an int, right? It's an int array. So it's a collection of, it's a byte address, but then, so yeah, my original address is 00, and then the next one is at 04 because I'm storing integers, and integers are 4 bytes by default. Yeah. All right, other questions? Okay. Yeah, in C, we pass by reference, pass by value. Um, the default is to pass by reference when we're using arrays and pass by value when we're using sort of the primitives, but we actually can choose to do it differently. And this, passing of pointers will be a lot more relevant as we go on. And the other thing is, well, this is exactly the same thing, right? So I changed the syntax. Now it's a pointer instead of using the array syntax. But in terms of what happens when I call it, exactly the same, except now it's more explicit, right? This is a pointer. So when I call this, I pass in the array address, and that goes in here. And then everything else is the same. Okay, so that's, yeah, that takes us to the end of language features. And so talk a little bit about programming conventions. This is just in terms of, again, like the computer doesn't care what your code looks like, right? But when I go to read it, I kind of care, right? It's nice when everything is sort of aligned and all of the indentation is the same, even though I'm not super great at it either. But the nice thing is we have IDEs that we can use. So we can just say, select all, and then please format it correctly. And then you get something that's nice. So, basically there are sort of universal conventions, or, well, maybe they're not so universal anymore, but we're going to define a few conventions for this class, and anywhere you work will have its own sort of style guide that you should follow. Right? So makes code easier to read, makes everything consistent, right? So if I see a certain, pattern or case, then I expect, if I see camel case, maybe I expect a class or a struct or things like that. For example, constant names, typically all uppercase, right? So max array or things like that. If I want to separate the words, right? If it's 2 words put together, I can use an underscore. Variable names begin with a lowercase letter. Again, I've seen every one of these rules broken, right? So this is defined for our class. It shouldn't, when you get out into a job, they'll have their own style guide. But if I have multiple words in my array, I can use camel case, right? Where I make a capitalize every word after the first one, or I can use underscores to separate the words. Names should be self-documenting without being overly long. I'm sort of a documentation minimalist. That does not mean no documentation, but it does mean that, for instance, if you have a big long comment somewhere in your code, that's probably not really the right place for it. First of all, as soon as you change your code, that comment becomes a lie. Right now it's deceiving. So yeah, so code that is sort of self-documenting, so where the names are meaningful, as short as they can be, but meaningful. is sort of the goal here. Right, so if I'm storing a name, I want to use the variable name and not just n. N is kind of weird. It could be anything. And I could use the scope as context, right? So if it's in a student struct, instead of student ID, I can just use ID, and people will pick up the rest. Yeah, single lowercase letters are commonly used for looping, so small I, small j, small k, etc. Data types or classes begin with uppercase. This is, of course, you're going to see tons of exceptions to this in C and C++, but we are going to use it. So when we make a, well, not so much a class, but a struct, we're going to start it with a capital and camel case or underscores if it's a compound name. Functions should begin with a lowercase letter, right? That'll help us identify it. Again, with the use of IDEs, now all of these things take on colors, right? So sort of some of this stuff becomes less important, but you know, it's still a good idea. White space before the first character of the line, right? So if I have some code block, like in an if block, then I should indent everything in there. And that makes it nice and easier to read. If I have nested blocks, if I have a for loop within an if statement or vice versa, then, you know, I should indent a little bit more, and then every sort of block at the same distinct pole should have, and yeah, basically. All statements within a block should have the same indentation, and all blocks at the same nesting level should have identical. The braces, you can choose one of these styles. Well, basically, I kind of mix them up sometimes, but this is if you only have, you know, a very short line of code, one line, but otherwise you can, you know, pick up your brace here or pick it up on the next line as you wish. Indentation, well, I choose something, stay consistent. I do find, again, the fact that I have an IDE that'll do this for me has been a blessing, because otherwise I'm going to mess it up. But block comments are used to explain the program, explain a class, or explain a complex or critical block or section of code. Well, so in some sense, I give you a document and I consider that document to be the specification. I don't need you to repeat everything that I put. So if you're doing something that is different from the docket, then you should document it, right? So if you do, and I encourage it, like try different stuff, but just explain it so the TA knows how to mark program. Block comments in the main function specify this. Again, I'm not really, I am a doc minimalist. This is important when you get out into the world. I'm not really going to mark it too much in this class, right? So a few comments, don't go overboard, and you'll get your marks. I'm mainly looking for nice readable code. That's the main thing I'm looking for. But yeah, it is nice. I mean, if you look at a well documented language like Java, right, where you have Java docs, and then a sort of a poorly documented language, which, I mean, there's a lot of them out there, but the difference can be huge, right? Like Java is such a pleasure to use because I can always look something up. Other languages, I look stuff up and maybe it's an 8, or I've actually used C++ mesh libraries that had no documentation, and that was a lot of fun because it's just guess and check, right? But it's, yeah. So ideally, again, I'm not big on comments because, well, it's hard to get marking consistent among TAs as well. Some of them are very enthusiastic and others not so much. So, but they are important. I'm not saying they're not important. They are important. Just not as important to me as running code, and code that reads nice. So yeah, I can, if I need a short explanation in line, I can do the 2 forward slashes. If I have maybe 2 lines, I can also use the 2 forward slashes. Anything more than that is probably a paragraph, and maybe I want to use this style where I use the /*. And, you know, these are cosmetic. You don't really need them, but they look nice, so we generally put them in. And yeah, so don't pass by value. We're gonna learn that, right? So structs or arrays should be passed by reference. So we saw that array was passed by reference. Now, if we pass by value, we can actually do it, but it makes copies. It's slow and wasteful of memory. Do reuse code wherever possible. Don't get carried away with this idea, right? So there are a lot of sort of these heuristics about what nice code looks like dry, which is don't repeat yourself. But I've seen these taken too far, right? So if it does not improve what your code compiles to, right? If it doesn't improve the sort of correctness, and if it doesn't improve readability, and it doesn't improve the ability to modify it in the future, then maybe you should think about whether you actually want to refactor this thing, right? So do think, like, there are these general heuristics, but do think about them before you apply them just liberally. But do basic error check, right? So that's a good one that you can always do, and it's never a bad idea. All right, questions? Yeah. Oh, yeah, we'll get to that. So, well, refactor actually is kind of like what we just did with that array program. So we had one big function, the main function where everything in it, and then refactor means I changed what the code looked like, but it still behaved exactly the same, right? So I refactored it so now I had three small functions, and in my main function like shrunk and was easier to read, and then I had three other functions that I could call, and that's refactoring, right? So nothing changed about the functionality, but it reads nicer, and maybe it's easier to modify as well. Right, other questions? Okay, let's look at some bits. So one of the yeah, I'm not sure. Somehow this looked better before. One of the things about, well, C is low level, and one of the things about low level languages is sort of how this data is represented. So we're going to talk a little bit about that today. I don't know who this person is, but I do like this quote: software isn't about methodologies, languages, or even operating systems. It's about working applications. So yeah, I do to give me working code. That's kind of really high on my priority list, is that it works, that it runs. If it runs, it's easy to mark. If it doesn't run, kind of really, you're going to get a few marks for like style and things like that, but I don't really want to mark a big mess of code. And especially with, sort of the weakness of ChatGPT is it can give you nice looking code that doesn't run, right? So make it run. That's sort of the bottom line. So we're going to talk about number representation. We're going to talk about bases, and then we're going to get into bit models. So basically, computer data is made up of bits. So how do we interpret it, right? So everything on your computer kind of looks like this. Like every piece of memory is just, it's holding a voltage. Either 1 means like 5 volts or something, and 0 means around 0 volts. So everything in the computer is just these discrete values, 0 and 1. All right, so now the question is, and this might be in RAM or it might be on disk or wherever. So what do we do with this information? Well, the first thing the computer does is it breaks it up into chunks, right? Just to be a little more organized. And you'll notice that each of these is 8 characters long, right? So this is called a byte. And on a computer, generally speaking, a byte is the smallest piece of data that is addressable, right? That means that I can ask for the data at this memory location, and it will return me that byte. I can't ask for any less than that, although there's tricks on, I can ask for the whole thing and then just look at the last 4 bits or something like that. So anyway, we have the data's partitioned, but we still don't know how to interpret it. Let's look at this little subset. So we have 3 bytes here, and there's a bunch of different ways we can interpret this, right? So we can look at this as 3 unique integers. So I ask the computer what's at this memory location, it returns this, and I print it to the screen, and it prints out 67, right? If I print it as an integer. And this one would be 79, and this one would be 87. Or I can put it all together and think of it as one large number, right? The same way that I could say, look at these numbers and say 67, 79, 87. Instead of interpreting it as three numbers, I can interpret it as one number just by cramming them all together. I can do the same thing with this. Of course, I get a different number because it's in a different base, which we will talk about, but it can be a word count. This gives me back the number 67. I can go into an ASCII table. The ASCII table, I look it up. It says 67 is associated with the character C. So if I print this out as a character, then I'm going to get C. And then I'm going to get, if I print out all three, I'll get cow. It can be a color, right? So RGB value, red, green, and blue. These are, yeah, well, probably most of you have seen something like this, where you can put in the RGB values and get back whatever color you're looking for. It can also be a real number, or what we call a floating point number, so something with a decimal. So yeah, how do we determine which of these it is? Well, basically it can be any of them. Usually the type of variable that we're using is how we interpret it. But let's first talk about some of the basics. So the numbers that we use are in base 10, right? So I give you this number. There's nothing special about it, but I can break it down into, say, the one column, the tens column, the hundreds column, the thousands column, right? And so that's kind of what I do here. In my ones column is 9, so it's 9 times 1. And then in my tens column is 8. So that's 8 times 10. And in my hundreds column is a 3, so that's 3 times 100. And I can break it down into this sort of addition of all of the digits and the value of their column. And this is equivalent to this, right? So 10 to the 0 is actually equivalent to 1. And this 10 is actually equivalent to 10 to the 1. 100 is 10 to the 2. And 1000 is 10 to the power 3, etc. So these are perfectly valid ways to write this number, or at least to get the same result. And so this binary that we see, these bits, basically do the same thing, right? So this is, if I write this out, 62389, this is worth 1, or this is 10 to the 0, and this is 10 to the 1, and this is 10 to the 2, and this is 10 to the 3. But in binary, let's say I did something like this, 1101. Instead of being powers of 10, these are powers of 2. So this is 2 to the 0, this is 2 to the 1, this is 2 to the 2, and this is 2 to the 3. So this would be 2 to the 3 times 1 plus 1 times 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 0, right? And then this would be, what is that? 8, 12, 13. Okay, so that's in binary, and binary is sort of the basis for our computer, right? Because it has all those bits. However, in addition to binary and decimal, which we use and the computer uses binary, we have some intermediate representations that are just useful for representing binary numbers. We'll talk about why, but so we've talked about a basis of 10 and a basis of 2. But if I talk about octal numbers, I have a basis of 8, right? So when I write an octal number, each digit is going to be somewhere between 0 and 7. And then it's going to be the 8's column, the 1's column, so 8 to the power 0, and then the 8 to the power 1 column, and then the 8 to the power 2 column. And the same thing with hexadecimal, right? Except now hexadecimal is base 16, and it turns out I ran out of numbers. So when I write a digit in hexadecimal, I'm going to include A, B, C, D, E, and F, right? So an example of hexadecimal is 4A, and that is basically, A is 10. Well, I'll save that for when I have more space. But yeah, A is the 16 to the power 0's column, and 4 is 16 to the power 1 column. Yeah. So if I have a number 1101, I can actually represent it in, what the value is. It depends on what base I'm using. right? Because 1 appears in all the bases, 2, 8, 10, and 16. So in base 2, it would be, well, we did this earlier. 1 times 2 to the power 3 plus 1 times 2 to the power 2. This is 0. So we get, well, that's not 77. Jeez Louise. I somehow got that wrong. All right, so there might be a couple mistakes here. Obviously, this should be just 7. Maybe I just hit the number twice. In 8, oh yeah, sorry, 13. All right, so I really messed up that number. All right, base 8, I would do something similar. 1 times 8 to the power 3 plus 1 times 8 to the power 2 plus 0 times 8 to the power 1 plus 1 times 8 to the power 0. 8. Anything to the power 0 is just 1, so it's always the ones column to start with. And I would have allegedly 577. Maybe that's correct. I would double check that. 10 is easy because we've been using it all our lives. So this is just 1,101. Base 16, yeah, I would do the same thing, but 1 times 16 to the power 3 plus 1 times 16 to the power 2, etc. Okay, so if we have, if we're only using ones and zeros, that could be a number in. All right, questions so far? Okay. Yeah, so octal and hexadecimal. So as mentioned, we use them because, well, binary and decimal. Oh, yep. Oh, yeah, that's a very good question. So yeah, this is actually worth 10, B is worth 11, C is worth 12, D is worth 13, E is worth 14, and F is worth 15, right? So in the sort of the ones column, I can represent any number. So let's say 4A would be, I guess let's do it. So A is, if I have 4A, I can write that as 4 and then 10, right? So the digit 4 and the digit 10, and this column is 16 to the power 0. So 10 times 16 to the power 0 is 10, and this is 16 to the power 1, and 4 times 16 to the power 1 is 4 times 16, or 64. So it'd be 64 plus 10. That should be 74. So 4A is equal to 74 in decimal, right? So yeah, very good question. Yes, I did neglect to put that on the slides. A, B, C, D, E, F is just continuing counting up 10, 11, 12, 13, 14, 15. Other questions? Okay. Yeah, so I mean, I'm going to throw like a bunch of examples and a bunch of like tables and all of this stuff, and hopefully some of that sinks in, but if it doesn't, ask and we can do some more examples. Okay, so if I'm, for instance, right, so I more or less know how to interpret this binary number, right? So for example, this is 2 to the power 0, this is 2 to the power 1, this is 2 to the power 2. 2 to the power 2 is 4, times 1 is 4, 2 to the power 2, or sorry, 2 to the power 1 is 2, times 1 is 2, and then the ones column. So this would be a 7, right? And if I had any other digits over here, I would just keep following that pattern. But now, everything to binary from decimal, well, I'm going to get some pretty long numbers, right? So binary is, right, this is 3 bits, and I can represent it using 1 digit in decimal, and that sort of pattern continues, right? So as I get huge decimal numbers, the binary numbers are going to be way, way bigger. So what I want is sort of a compression algorithm, a way to compress this information, but still kind of keep close to the binary. So for instance, if I used base 8, well, each digit is a number from 0 to 7. And if I look at all the possible representations of 3 bits, this gives me, well, if I have 0, 0, 0, that's 0, If I have 0, 0, 1, that's 1. 0, 1, 0, that's 2. 0, 1, 1, that's 3. 1, 0, 0, that's 4. 1, 0, 1 is 5. 1, 1, 0 is 6. And 1, 1, 1 is 7. So it turns out with 3 bits, I can represent 8 numbers, right? And in my octal, I have base 8. So I can represent 3 bits using 1 digit in octal. Exactly. So I have a 1-to-1 bijection. So this would be the digit 7, this would be 0, and this would be 0, right? So 7 in binary is actually, or sorry, 7 in decimal is 111 in binary, which is actually just 7 in octal. If I do this more complex example, well, I have, this is the 4's column, this is the 1's column, so this number is actually 5. So the octal digit that is represented by these 3 bits is 5. And in my next 3 bits, well, I just kind of start over, right? I want to know which digit from 0 to 7 is represented. And if I do the math, it's exactly the same. So I have 5 here. And then I don't have 3, I only have 2, but I could still represent that with an octal digit, right? It's only going to be a number from 0 to 3, but I can easily represent that. So this is 2. So that number in binary is 255 in octal. Okay, does that make sense? Questions? All right. This is not, I get it, it's a little bit mathy, but it's, you know, it kind of is important. Hexadecimal is the same thing, but we can compress it even more. In fact, 4 digits. If I look at the maximum number, the minimum number I can represent with 4 digits is 0. The maximum is what? 4 binary digits. What's the biggest number? Yeah. Nope. What's that? Sorry. Close. Nope. 15. Yeah, 0 through 15. And then it's 16 digits total, right? So starting with 0, counting up to 15, I have 16 digits total. But 0 through 15, this is, of course, in hexadecimal, this is 0, and in hexadecimal, this is an F. And I can represent all the numbers in between 0 and F, basically. So I have, with 4 digits, I have a number from 0 to 15, which corresponds to one single hexadecimal digit, right? So this is 1 plus 2 plus 4 is 7. So this is a 7 in hexadecimal, and this is a 0. So yeah, this is still a 7 in hex. But this one down here, well, this is what? 12, 13, and that is A, B, C, D. That's a D in hexadecimal, 13. And over here, I have 8 plus 2, which is 10, which is an A. So this is an AD in hexadecimal is this number in binary. Okay, so we use octal, and not so much, I don't see very much octal occasionally, but I do see, you will see a lot of hexadecimal, right? Because it is nice. 2 digits represents 8 bits, which is a byte, which is you know, something that is used quite often. Yep. Yes. Yes, I can. So I add up 8, 4, and 1. That gives me 13 here. And this is a 10. And then yeah, you got it? Okay. And then I just match them up to, yeah. Other questions yet? Nope, we only go up to F. So after that, we wrap around, right? So the same way that I go from 0 to 9, and then if I add one more, I get 10, but I don't really use any new numbers. I just have I just use 2 digits now. So if I count up all the way to F, right? So this is let's say I'm counting in hex and I go up to D, E, F, and then after F is 10. But this is actually like 16 in hexadecimal. Yeah, other questions? All right, so we can convert from octal and hexadecimal decimal as described earlier. I mean, we should be able to, we kind of should be comfortable with any base because all it is really, I take the base, I raise it to whatever power of whatever digit I'm at. And then, well, this is just, this column is 5 times 8 to the 0. 8 to the 0 is 1. This column is 2 times 8 to the 1. 8 to the 1 is 8. And this is 1 times 8 squared, which is 64. So if I add those things up, 1 times 64 plus 2 times 8 plus 5 times 1, I get 85 in base 10. Right, and I can do something similar in base 16 in hexadecimal. So this is 5 representations of the number 1. This is 0 times 16. This is plus 11 times 256, or 16, plus 2 times 4096. Right, so this 2B05 is actually 11,013 in base 10. Okay, questions? Okay. Yeah. We're just converting. So this is just because I might ask you that on a test, you know. So yeah, you should be able to convert between any like base 8, base 16, and base 10. Right, so we're gonna talk. Yeah, so I'm converting, this is an octal number. So this is base 8, and I'm converting to base 10. Yeah, so yeah, let me explicitly go through this. So this is, I look in this column, this is my, a to the power 2 column. It's 1. Whatever the result is, this is, it's 2 times whatever the value of that column is. The value of this column is 8. It's 2.
Like 8 to the power of what, 1, 2, 0, whatever, to convert to the base of 10 to binary. So we are using, we know we are octal.
Yeah.
Going to decimal.
Yes. We're skipping binary. You want to go to binary first? You can do that. Yeah, absolutely. But we're just not. Like we're just right.
Straight up, if you just go 8, take it to the power of.
Yeah, exactly. So yes, we use these. So we don't need base 2 here at all. These have their own rules. We use them because they are nice to transfer to base 2 and back. That's why, right? Especially hexadecimal. 2 digits is a byte, and that's really, really handy. Which of these do we actually need to know? I need to know all of that, right? That's all testable material. It's actually real easy to make test questions on this. So yeah, I'm happy to answer more questions. But this will be something that it will appear on the first midterm, stuff like this. Yeah. Just to make sure you understand that base 10, that's all. Yeah, this is it. Yeah. Other questions? Yeah. Oh,
Wait, hex to decimal.
yes, you're right.
That's what I was wondering. Why is it base?
Oh,
I was confused by.
yes, sorry. Yeah, I got that. I'll make a note of that. Yes, so I've been, I don't know. I'm creating these at very fast speed, so there might be mistakes. Yeah. Which sort? This is base 10, yeah. So this is, I mean, normally I would just write it like this, right? Just 11. So if it's just me and you talking and this is not a computer science class and I say 11,013, that's, you know what that is. And that's all that's all the base 10 means is this, I'm just telling you that this is not like octal or hex, this is base 10. So yeah. So if yeah, a little subscript here just means that's the base. Well, you can, I mean, if it says convert to decimal, I'm going to assume you're writing a decimal, right? So, yeah. Yep. You could do you could do this exact process with binary as well, right? It's just now instead of 16 to the power 3 and 16 to the power 2, this is 2 to the power 3, 2 to the power 2. But, and also I will only have zeros and ones there. Yes, that's coming up. But you guys use calculators, eh? Just, yeah, that'll be fun. Well, maybe that's not a great idea because your calculators these days can do everything. Probably no calculators. It'll be easy questions. So converting, how do I convert from decimal to binary and decimal to hex? Well, I just divide repeatedly and take the remainder. Okay, so if I have a decimal number, 235, I'm going to divide by 2 until I get down to a half. And then I'm going to take the remainder each time. So, or another way to look at it is 235, it's odd, which means the last digit is a 1. So 235 mod 2 gives me 1. And then I divide by 2 again. I get 117. This is an odd number. So 117 mod 2 is also 1, right? So let's go through the complete example. So 235 integer division, divide by 2, I get 117 plus 1 remainder, right? So the 1 remainder is the digit of my binary number. Then I take this number, this new number that I got, I divide by 2 again, and I get 58. And again, I have a 1 as a remainder. Okay. And now I take my 58, I divide by 2, I get 29, but now I have a 0 remainder because 58 is even. 29 divide by 2, I get 14 with 1 remainder. And yeah, I keep doing that until I'm left with either 1 or 0. And then, well, actually, I keep doing it until I'm left with 0 remainder. Right. What's that? No. So yeah, I keep going until I'm down to that 1 or 0, basically. And then I'm done.
What is it? Odds will get 1, evens will get 0.
Yeah. So basically, if the number is odd, so at this stage it's odd, so I write a 1 and then I divide by 2, right? With integer division. So I'll throw away the remainder. And yeah, so you can go through it like that as well. There's lots of little tricks once you learn this for how to get this number, but yeah. Other questions? I'm sorry? With what? Long division? You would have to do it repeatedly, I guess. I'm not sure what sort of algorithm you mean. You could use, I mean, long division will give you the answer, right? But yeah, I guess that would work, yeah, because you would get, yeah, yeah, if you did it correctly, I guess there's some version of long division that would work for this. Yeah, you would use a specialized algorithm, but yeah. I could do the same thing with base 16, right? So if I have a number 4,235, I do integer division, I divide by 16, right? Because I want to see, basically the ones column is going to be the remainder. So I divide by 16, I have 11 remainder. 11, I'm going to write as a B in hexadecimal. And then I have 264. I'll have to, I mean, this calculator thing, I'll have to think about, okay? If there's no calculators, you will not get something this hard. I will probably not ask you for something like this. That would be a little ridiculous. We'll see. But I have to see what your modern calculators can probably convert between bases pretty easily. I guess I can always ask to see your work, eh? Maybe that works. Maybe that's a good compromise. But yeah, same thing. So I have 264 remainder 11, and then I take 264 divided by 16. That is equal to 16 with a remainder 8. So I write 8 here, and then I take my 16 and I divide by 16. I get 1 with the remainder 0. So I write a 0, and then 1 divided by 16 is 0 with remainder 1. And then I'm done. And then I sort of, this is the least significant bit, and this is the most significant bit. And by that, I mean the least significant bit is the ones column, and the most significant bit would be whatever the highest column I'm dealing with. In this case, it would be 16 to the power 3. Right, questions? Okay, we can represent all of these in C. So this is a little program that we're going to run. But basically, if I wanted to do these conversions in C, I could do them. What's that called again? Bases. Oops. Yeah, so let's load that in. Okay, so this is the code that we saw, and basically, so here I'm taking an unsigned character, right? So we'll talk a little bit about what that is, but it's basically a byte. So I can store any number from 0 to 255, and I'm going to store 27 in decimal. Now, if I want an octal number, I'm just going to put a 0 in front of it, right? So the C program will convert this into octal. This will 7 times 8 to the power 0, which is 7, plus 2 times 8 to the power 1, which is 16, right? So this should convert to 23. If I want hexadecimal, I do 0 x. And I'm going to use a small x here. You can use a capital X as well. In this context, it's meaningless. I believe it's, if I use the capital X, then I'm going to use capital B, capital F, and things like that, right? So, wait, is that right? Let's test that out. But 0x or 0x means hexadecimal, and then I can follow it with my hexadecimal number, which means I can use 0 through 9 and A through F. Here's a second hexadecimal number, and I can do binary, which is 0b followed by my binary number. Long hex. So my long int is basically 8 bytes, so I can store a much bigger number in there. And I believe that might be 8 bytes as well. We import libraries for the assignment only if, I mean, I guess math if you want, but other than that, probably not. Just run it by me or a TA to be sure. So yeah, now we can print all of these numbers and see what they're converted to. This means the long unsigned int. Yeah, that's the. Oh, sorry. I guess I put it in the wrong place. Oh, okay. Okay, so yeah, 27, 23, 191, we can compare these to our code here. Yeah, so the 27 in decimal is of course 27. 027 in octal is 23. The BF in hexadecimal is 191, and BAD is this. This is 60, and this long hexadecimal number is this. And I don't know, I'd have to count to see how many bytes that is. That might be the maximum you can represent with a long. But yeah, I would have to double check that. So yeah, C will do all these conversions for you if you want to use bit manipulation, right? Which we're going to do in assignment. Questions? Yep.
Represents a hexadecimal value.
Yeah.
If it's just the zero in front of it, then that's an octal number.
Right.
The zero B in front of the zeros and ones is marked binary data.
Correct.
Something just a regular decimal.
And then, yeah, if it's just a number, it's a regular decimal, right? So if there's a leading zero, be careful because I mean, it still looks like a decimal, but it's actually octal in C. I do want to try this actually. So when in doubt, test it out. So yeah, you can use a capital X here, and I believe you can use capital B and F as well. Yeah.
The difference between your printf there and printf here. So would both work because you have LU and LD.
D, yeah. I was experimenting. I forget. I would have to look up what the D stands for. But I was, you know, after I was.
Because the way it's written here is
I think this is again, I would have to look it up. It might be this might be a long signed integer. But I'm not sure. I forget. Yeah. I never remember these things. I always have to. Yeah. All right. Other questions? Let's try and move a little bit. So why do we have a B character in the binary one? Because otherwise we can interpret that as well, if we didn't have a B character, it's you know, I don't know how to use Windows. So yeah, if I didn't have a B here, then this would be an octal, right? So the 0B tells me that it's a binary.
decimal we have 27, but if we want to do a decimal that starts with a 0, but we want to put it as an octal, so would that work or no?
What do you mean if you have one that
For
starts?
example, binary is 0, 0, 1, 1, 1, 1.
Right,
For example, if this was a decimal,
right.
and we write it as an octal, would that be a thing that can happen or no?
I'm still not quite sure, but I mean, the binary is special. I could do this as well, right? That doesn't change the outcome here. It just looks nicer if I put the leading zeros. But yeah, the 0B tells me it's binary, and then if I put whatever leading zeros here I want. But yeah, outside of that, leading zeros is sort of dangerous because now it's an octal. Yeah. All right. Okay, so bit model. So that takes us, that's basic binary bit model, right? So we're going to see that's actually a magnitude only bit model, right? So we talked about we're reading binary numbers and how we interpret them. Well, that's one way to do it is just sort of literally. I just take the value, right, in base 2, and that gives me a number. So in binary numbers, each 1 or 0 is called a bit. 4 consecutive bits is called a nibble. I have never heard that used ever once, but except for here. But it's kind of useful because we can think of a nibble as a single hexadecimal character, right? So it's somewhere between 0 and F. 8 consecutive bits is a byte, and you will hear that all the time. And a byte is 2 hexadecimal characters. Incidentally, when I was a kid, I played on a Commodore 64, which was just a wonderful computer at the time. Wow, I'm really dating myself, but funny story, if I wanted to play a new video game, well, first of all, we stole them, right? We passed around discs and copied them, and that was big business back then. But the other thing you can do is buy a gaming magazine, and on the gaming magazine, they would have pages and pages of this. FFA034, blah, 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 which was just all of these hexadecimal numbers that you can then write into either a special program like an assembler, or you can just poke them into memory. And basically this was an assembly language program, pages and pages, and it was almost impossible to get to put them in without messing something up. So I'd have all these like half-formed games that really didn't kind of worked maybe sometimes, but mostly like things didn't look right and stuff like that. But yeah, they're fun times. A word in a computer is a size, it means a lot of things, but generally speaking, it's the size of the data your architecture revolves around. So often what it'll mean is the size of your data bus and the size of a single CPU instruction, right? And often it is 4 bytes. Can be the size of registers, but registers have a bunch of different sizes on your CPU. So none of these things are necessarily true, right? So architectures can mix and match things and do whatever they want. But generally speaking, it's the size of your bus and, usually the size of 1 instruction. So yeah, 32-bit architecture, it's 4 bytes, and a 64-bit architecture, that's your word size, right? It's 8 bytes. So when we look at a word, we interpret it based on the context, and then based on that context and the bit model, we can retrieve a value, right? So there's magnitude only, there's sign magnitude, there's 2's complement, fixed point bit model, floating point bit model, and ASCII. In C, we use magnitude only. We do not use this one. We use 2's complement. We do not use this one, although that's, well, we got some stories about using that one. But so yeah, we use magnitude only, which we've already seen. We use 2's complement, which we'll see we can use for negative numbers, which is for, decimals, 1.012, something like that. ASCII and Unicode is for characters, right? So if I want to write a string, I'm going to take a bunch of numbers and convert them into ASCII. In C, the type of model used depends on the data type. So an unsigned int would use the magnitude only, but an int can represent negative values. So we would use something like 2's complement. C does use 2's complement. Float obviously uses the floating point bit model, and character uses ASCII, I guess, or Unicode, although I'm not as familiar with Unicode. So yeah, magnitude only is the simplest one, and we've seen it already. It's just base 2. So I take some bit or some byte or some collection of bits, and I just, this is the least significant bit, and it's the 1 column, and the next column is the 2's column. The next column is the 4's column. So this is our most significant bit because it carries the most weight, and this is our least significant bit. Right, so in a byte, an 8-bit value, which is what a character typically is, a char, we can store a number from 0 to 255. Right, so 0 is all zeros, and then we can just start counting up. until we get all ones, which is 255. Adding in magnitude only, easy. It's, yeah. It can be represented by a hex character, right? So this is a byte or 2 nibbles, and this can be represented by a hexadecimal character. This is a 6, and this can also be represented by a hexadecimal character. That's a 1, right? So a nibble can be represented by a single hexadecimal character, like the value. A nibble is a value between 0 and 15, whether it's binary or hex or whatever. Does that make sense? And then a byte is a number between 0 and 255. And a byte, yeah, a byte I can represent with 2 hexadecimal digits. Or, you know, I can write it in decimal. So what's that? These are bytes, yeah. These are 8 bits, these are bytes, yes. But yeah, a byte is just, if you want it to get really abstract, it's, why is that not working? It's a value between 0 and 255, and that's about it. And it just happens to be 8 bits. Or 2 hexadecimal, or however many octal. I think it's 3 digits, but the last digit doesn't go quite all the way to the top. Addition, same thing we would do in decimal. So 0 plus 1, I'm going to add each column, so I get a 1 here. 1 plus 0, I get a 1. 1 plus 1, I get, what do I get? It's 2, right? But how do I write 2 in binary? This is 2 in binary, right? Yeah. Yeah, so I'm going to carry a 1. So I've overflowed. If I add 1 plus 1, incidentally, this is the shirt, right? You see a lot of computer science people. There are only 10 types of people in the world, those who understand binary and those who don't. You might see that occasionally. So this is a 0 plus 1 overflow. So this goes here. I add 1 plus 0 plus 1. Again, that's a 1, 0. So it's a 0 plus a 1 overflow. Now I have 3 ones. So this is in some sense 11, right? So 1 plus 1 plus 1 is 3. In binary, it's 1, 1. So I have a 1 digit here plus a 1 overflow. And then I have 1, 0, 1. So that's how I would add them. Exactly the same as I would do in decimal, except for I overflow on a 2 or a 3. Here I would do the same thing. 1 plus 1 is 0, 1, 1, 0. Now 3 ones, so it's a 1, carry the 1, 0, 0, 0, 0. Uh-oh. So I've added 2 bytes, and I added 2 8-bit numbers, and I ended up with a 9-bit number, right? So if this is on a computer, this can be a problem. Well, not really a problem, but I have to account for it now because it's not going to fit neatly back into a byte. So generally speaking, there's an overflow register on your CPU that tells you when something like this happens. All right. Okay, so 1 byte, number between 0 and 255. However, I can, you know, if I want to store bigger numbers, I can use 2 bytes, or in this case, 4 bytes. So 4 bytes is typically what an integer represents. And I can, well, I've done some fancy math here, right? So I've said this number times 2 to the 24. So basically I have 100110001 times 2 to the 24 is I add 24 zeros after, right? Which is basically just gives me the, you know, sort of the correct column for these digits. And then I did the same thing here. So this is this number, but moved 16 decimal places to the left. So I add 16 zeros to the back. And here I add 8 zeros, and here I add 0 zeros. And basically that's why, I don't know why that's not working, but yeah. And then if I add all of those numbers, I get, well, now I can convert this byte into 153 and 2 to the 24 times this number. So I've done, I could have taken each column individually. This is kind of short, even though the math is still ugly. But yeah, this is another way to convert a large binary number into a decimal. Maybe you understood that, maybe you did. I'm not going to ask you this on a test, but questions? Yeah. Yeah. Yes, exactly. Yes, it's that one. Right. And I mean, if I did the same thing in decimal, let's say I wrote 888,333. Well, that's 888 times 10 to the power 3, right? I'm writing that. I'm just shifting the decimal. I'm shifting it to the left. I'm adding zeros, 3 zeros to the end of it. And then I'm adding that plus 333 times 10 to the 0. So that's all I kind of did there. Yeah. Yeah, so that's right. So I don't know why my eraser's not working, but it's getting a little messy. Are you kidding me? Okay, so what happened? So let's say I did the same. So let's put it into a decimal analogy, right? So I just have I have this. So 888,333,222,111. That's a decimal number. So how am I going to write that? Well, I take 888 and I say, well, that is equal to 888,000,000,000 plus 333,000,000 plus 222,000. So to get this number, I had to multiply times 10 to the power 9. And I'm just doing the same thing here. I'm taking these digits and I'm putting on 24 zeros after it. Because it's bytes. Everything in computer revolves around bytes, basically. So bits and bytes, not so much nibbles, but yeah. Does it make sense? Bytes have 8 bits. Yeah. Yeah. So I'm moving this sort of 3 bytes to the left. 3 bytes is 2 to the 24 values. Is there a place where you can do it? I'm almost certain there are plenty of resources for doing this. I would have to look some up though. I mean, you can try Googling it, but I mean, this is quite a common, I guess, computer science lesson, right? At some point, everybody kind of hits the bits and bytes and how you convert. So yeah, just before we end, so given these sizes, we have a bunch of different ranges that we can represent using the magnitude only model. So just a single byte is a number between 0 and 255. If I have 2 bytes or a 16-bit word, that is 0 through 65,535. 32-bit word is typically what your integer is. So it's 0 to 4 billion and something. And 64-bit, that's massive. So yeah, so next class, we will start getting into other representations, negative numbers, floating point. And yes, it's going to be a bit of a grind. It's a bit mathy in this part. So yeah, I apologize, but I will see you guys on Thursday.
Simon. The thing about like sneaky 2 and sneaky 3, because like you don't provide it. What I did with sneaky 2 was just copy all the code I did